model part, okay, we've learned about many equations. So all of this equation actually is the same to the equation that you used during your primary school. It's just that the symbol could be slightly different. Where now, instead of initial velocity previously in primary school, you are going to use symbol U, right? Initial velocity. This time around is going to be V initial. It could be in terms of X or Y. Okay, like this one, right? And then some of the book also probably can put it as a V naught. Right, it means that initial velocity as well. Okay, and what else? If it is one is in X direction, then we're going to have X. Okay, if it is in term of, this one is X axis, along X axis, yeah. If it is along Y axis, then you're going to be the U equivalent to Vy initial or Vy naught. Okay, this is for initial velocity. For final velocity, in primary school you use symbol V. Now onwards, it's going to be V, okay, final in terms of x-axis, okay, or V only as well, right? And what else? For acceleration, you have, primary school is only A, but now onwards you have A along X or A along Y. Okay, this is Y axis and this one is X axis. For the Vy, or sometimes it's just V. All of this equation 1, 2, 3, 4, 5 here, okay, only can be used whenever the A here, from here to here, the A is equivalent to a constant value, or we call it uniform acceleration. If the A is not uniform, okay, or you are talking about instantaneous acceleration, all of these formula are not valid, cannot be used for instantaneous. Alright, in terms of motion diagram, okay, we can imagine the motion of the object is like this, from one position to another, okay, and then the velocity is increasing, okay, linearly, right? The arrow is keep on increasing linearly, and if you see here, the arrow representing the A is constant value, right? The length of this arrow is the same throughout the motion of the object. Example 2.7, carrier landing. A jet lands on an aircraft carrier at a speed of 140 miles per hour, which is more or less 263 meters per second. A. What is acceleration assumed constant if it stops in 2 seconds? Right? Due to an arresting cable that snags the jet and bring it to stop. Okay, so A equivalent to along X, yeah, because the jet's moving along X axis, let's say, X the jet is moving along X axis, so A is actually delta V over delta T, which is Vx. When we talk about delta, it must be final minus initial over the time taken, which is finally it stopped, initially start at 63 meters per second, over the time taken is 2 seconds, so you have negative 32 meters per second squared. What was that by negative? It's decelerate. because finally it stopped. Right. Part B, if the jet touches down at position x equivalent to 0, what is final position? Okay, so now we want to know the final position of the jet. So we have delta x equivalent to Vx initial plus Vx final average over 2 times T. Okay, then you are going to have x final, x initial plus half x initial plus Vx final T. So 0, touchdown at 0 plus half 63 initially, finally 0, the time 2 seconds, which give you 63 meter after final position for the jet. Okay, suppose the jet lands on the deck of an aircraft carrier with a speed faster than 63 meter per second, but has the same acceleration due to the cable as the calculated in part A. How will that change the answer to part B? So mean that we need to figure out the x final for the jet again, but then with the condition given. X final equivalent to x initial plus half Vx final Vx initial times T. If according to this, if the speed faster, x initial, we know this one is 63. Okay, in previous calculation, this one is 63. Finally 0. If this one is bigger, it means that this one going to be bigger as well. It's directly proportional, right? So, because the question asking of how will, in terms of interpretation, the position, okay, or the x final, okay, will be larger. How big? We don't know. We cannot calculate because it's not given the value. It's just that faster then. Okay, so indication of this is actually directly proportional. So if this one is bigger, then this one also going to be bigger or larger. Example 2.8. Okay. So you are driving at a constant speed of 45 meter per second when you pass a trooper on a motorcycle hidden behind the billboard. Oh, speed trap. 1 second after your car passes the billboard, the trooper sets out from the billboard to catch you, accelerating at constant rate of 3 meter per second square. How long does it take the trooper to overtake your car? So to overtake, if you refer to this diagram, right, to overtake our car, okay, at least the trooper need to be at the same position finally. This is the minimum requirement to overtake, okay, a car. At least the trooper going to be at the same position to the car finally. This is the minimum requirement. So with that information, okay, we're going to figure out the x of the car, the x final of the car, the x initial of the car, which is at the billboard, plus Vx of the car times t. Right. So how about the trooper, the x final equivalent to x initial plus, this is the equation, x initial t plus half 80 square. Right, for the trooper, okay, initially is exactly at the billboard. Therefore, we define 0. Okay, because the motion of the trooper start from the billboard, and the billboard is our reference. Okay, that's why we set the x initial of the trooper becomes 0. Okay, plus Vx initial of the trooper, this is for trooper, trooper. Okay, start from rest, so it's 0 again, plus half ax t square, because it's moving along x, right? And the condition to have them to have the overtake to take place, to happen, okay, x of the trooper must equivalent to the x position final of the car. Their position must be the same. Okay, the trooper only have half ax t square. The car is positioned at B plus Vx of the car times t. Okay, so rearrange of this equation. Figure out for the t. Okay. Rearrange the equation. Half ax t square minus Vx of the car t minus x of the car at billboard equivalent to 0. So t equivalent to Vx of the car plus minus quadratic, right? So we have to use quadratic solution. Vx of the car square plus 2a x and then xp at the billboard, the car at the billboard, square root everything here, divided by ax, right? So from here, Vx of the car over ax equal plus minus square root of Vx of the car square over ax square plus 2xb over ax. Right. Finally, t equivalent to 45 over 3 plus, let's say, square root of 45 square over 3 square plus 2 times 45 over 3 square root of this, which give you equivalent to 31.0 seconds. Another part is, what if the trooper had a more powerful motorcycle with a larger acceleration? How would that change the time at which the trooper catch your car? If it has powerful, bigger acceleration, powerful engine, bigger acceleration, so the t will be less than 31 seconds just now, isn't it? Because of this information, t equivalent to Vx of the car over ax plus square root of Vx of the car square over ax t square ax square plus 2xb over ax, because of this, right? Free falling. So Galileo famous gravity experiment is actually Galileo. It is said that Galileo released two objects, and the object reached the ground almost at the same time. However, actually there is existence of air friction, right? If you drop feather and coin, it won't reach the ground at the same time. However, if you really make a space, a volume without any air or vacuum, completely vacuum area or volume, and you drop a coin and a feather, you're going to fall down and reach the ground at the same instant. So this case we call it free falling object, whereby we assume there is no air friction at all. Okay, and the object is freely falling towards the ground due to the gravitational acceleration, or simply known as gravity. 2.10. A stone thrown from the top of a building is given an initial velocity of 20 meters per second straight upward. The stone is launched 50 meters above the ground. The stone just misses the edge of the roof on its way down, as shown in figure. So in this figure, okay, initial position of the stone from the ground is actually already have 50 meters up above the ground. And then initially, okay, the moment the stone is thrown upward, okay, its experience V initial along y-axis 20 meters per second, and then the gravity is negative 9.8. Alright, so the final position, okay, initial position at A is 0. Okay, initially T at point A is 0 as well. A, using T equivalent to 0, T at A, as the time the stone leaves the thrower's hand at position A, determine the time at which the stone reaches its maximum height. The moment, okay, this is the thrower, so the stone is moving upward, okay, until it reaches certain maximum height, and it is going to fall down and reach the bottom. So at the starting point here, okay, we take as the origin, set as the origin. This is X, this is your Y. The A of the stone will be along AY, which is equivalent to negative G, which is equivalent to negative 9.8 meter per second squared. Why is it negative? Because, okay, the moment here you have V initial, okay, the V and the G is in opposite direction. So the A direction will be according to the delta V direction, because the A is defined as delta V over delta T. So the T has no direction. So the A direction is according to the V direction. However, the V and the G is in opposite direction. The G always to the center of the earth. Okay, we never fall away from the earth. We must be fall down towards the earth. Okay. So this is the first thing first. We consider there is no air friction. Air friction, okay, does not exist. Okay, before we proceed with whatever calculation. Right, so now I'm going to calculate according to the question asked for. When it reaches maximum height, by the way, okay, it's going to stop a moment. At this instant, V at this position 0 is going to stop a moment, because it's already maximum height before it fall down or turn downward. So, okay, Vy final equivalent to Vy initial plus Ayt. Right, so your interest is T equivalent to Vy final minus Vy initial divided by A along Y. Right, okay, so your T, okay, 0 finally, okay, at maximum height, the V is 0. So it's 0 minus initially 20, okay, and then the AY is negative G, which is negative 20 over negative 9.8 meter per second. So T equivalent to 2.04 second. Find the maximum height of the stone above its final position through the situation of the ball. Okay, at this maximum height. So V initial here 20 meter per second, right? And then V here 0. Okay, here as x-axis, here as y. T for this side to move from point A to point B. Here is point A, here is point B. It takes 2.04 seconds. Right. So now, Y maximum. What is Y maximum? Here. Y max. Okay. Y maximum equivalent to Y at B minus delta Y, right? YA equivalent to V initial. So, this one is 0, starting from 0, right? So, VAT is 20 meter per second times 2.04 that we calculated in part A just now, plus half negative 9.8 T squared 2.04 squared. Right, then you're going to have 20.4 meter is maximum height. Okay, from this information is here 20.4 meter. And C, determine the velocity of the stone when it returns to the height from which it was thrown. So means that from this position moving up and then falling down. So this is 20 meter per second. Here we have V here 0, and then the time taken T here must be the same to the time taken when it reached the same level here. Okay, you can simply say that, or you may do the calculation to show that or prove that. Now we need to determine the velocity of the stone when it returns to the height which it was thrown. So this position now, we put it as position C. Okay, so we are going to use V squared, V final squared, equivalent to V initial squared. Okay, so V final here, V at point C. V initial here is V at point A. Plus 2A along Y. S. The S is delta Y. Right. So 20 squared plus 2 times negative 9.8. Delta Y going to be 0. Y. Starting from this position, ending also at the same position. So Y initial and Y final is the same thing. So delta Y equivalent to 0. So you're going to have 400 here, meter squared per second squared. If you want to have V only, you're going to have negative. Why is it negative? Because of moving downward. So negative direction. So you're going to have negative 20 meter per second. it means that, okay, at the same position level, okay, the velocity, the initial velocity and the velocity here the same, which is 20. It's just this one is positive because it's moving upward, and this one is negative because it's moving downward. D. Find the velocity and position of the stone at t equivalent to 5 seconds. V at point D is equivalent to V at point A plus AYT, right? V equivalent to V naught plus AT. We are using that equation. So you're going to have 20 plus the A equivalent to negative G, 9.8, alright, and times with the 5 seconds. You are going to have the answer here, equivalent to negative 29 meter per second. Okay. So this is for velocity. For the position, y at D equivalent to y at A plus V at A T plus half AY T squared. So from which equation is this one? Is delta Y equivalent to V naught T plus half AT squared. So we rearrange the delta Y, the Y initial, we put it on the right side. So it's 0 plus 20 times 5 plus half negative 9.8 and then 5, because given to us the t is 5 seconds, right? Squared. So it's negative 22.5 meter. What does that mean by negative? It's downward or below the origin. Okay. What if the throw were from 30 meter above? None of the answer. Why? Mathematically, if we look back over our calculation, we see that we never entered the height from which the stone is thrown into any equation. Take a look. Okay, take a look. So, did we put 50 for calculation in part D? Nothing, right? Okay. Did we put any information of 50 meter? No as well. Did we put any information of 50 meter? No as well. Did we put any information of 50 meter? No as well. That is why from A, okay, until D, okay, nothing going to be changed. Okay, so it's regardless of 30 meter. Because of the time also, okay, it's a 5 second, okay, above the ground within the flight. Alright, okay, now almost the final parts. Okay, we want to have to take a look on the kinematics equations for motion in one dimension derived from calculus. Okay, so if you refer to this graph of Vx versus t, okay, it is in terms of curve actually in real motion. So if you figure out the area under the shaded, okay, rectangle is equals to the displacement in the time interval, because you have V versus T. So if you figure out, let's say, an area for the shaded area here, okay, how to figure out the area equivalent to the V, okay, times with the delta T. Okay, the V times with the delta T for one particular or order of delta x. You will get delta x by multiplying V with the delta t. If you want to have a total of delta x, okay, from t initial up to t final, what you're going to do, you're going to do summation of v with times with the delta t. Alright, so when you are doing summation of, means that you are adding them part by part. Okay, the small part here, one by one until the end of t final. This is also the same meaning to this one, meanings that you are doing the limit, okay, of your v to the respect of time whenever your t is approaching 0. Okay, meaning that you are doing part by part, small part of t until the t is very small. So, okay, this one also the same meaning with this. Okay, the delta x now also can be written in terms of integral or antiderivative of vx, okay, as a function of times, because it's vary according to the time, to the respect of time. Right, so this is on how we derive the equation, kinematics equation, from calculus. Alright, let's take a look at a few more. For A, acceleration, okay, is dv over dt in terms of x-axis, in terms of x-axis. Goes the same for y-axis. If you rewrite this equation, you will get dv equivalent to a dt. dv, what does that mean? It's actually v final minus v initial, okay, equivalent to integral of or antiderivative of acceleration to the respect of time, where the time begin from 0 until the t that we are interested in. Okay, so this one also can be written as, if you are doing, let's say your a is constant, your a, okay, a here, ax here, a constant value, okay, then you can bring the a outside of the integral process, okay, integral function, okay, then the a, the one that going to be integrate only dt. Okay, so you're going to have ax times with a t minus 0, because the limit of the integral function 0 up to t. This is final, this is initial. So you are going to have axt. The common formula that we are used to, okay, means that vx final minus vx initial equivalent to axt. Alright, or we are used to this, vx final minus vx initial over the time taken. Then you will be familiar, you should be familiar with this form, isn't it, instead of this form. Actually, they are the same thing. Okay, then for the vx, we may also put it in terms of this. Okay, as we know, what does that mean by velocity? It's change of position over time taken to have that change. If you rearrange this derivative equation, you will get the x equivalent to vx dt. What does that mean by this? This part is this one, and this one, okay, can be written in terms of integral or antiderivative vx t to the respect of t, where the limit is 0 up to t. Alright, so if we're talking about vx, which is equivalent to vx final equivalent to vx initial plus ax t, this is a common that we use to. Right, so from here, okay, our vx is this one. Okay, from here we rewrite this equation. Okay, so we have x final minus x initial equivalent to integral of, what is our vx final, which is this one, the whole bulk of this. Okay, put it here. Right, so you will get, okay, integral of vx initial plus axt to the respect of the time, where the limit is from 0 up to t time. Right, so open up this one. Okay, you can have in terms of this pattern. Now, okay, this is a constant, bring it outside in front of the integral function, and then this one also a constant, bring it in front of the integral function, then you're only going to integral the t. So you have here, with the limit of 0 up to t, vx initial times t minus 0 plus ax. So here only you have t, right? So when you integrate, let's recall, you're going to have t squared over 2, like this one. Okay, minus 0, because second part is the initial part, the condition of the time is 0. So from this pattern, you rewrite this equation, okay, into this, okay, where we are familiar with this one, actually the same form of delta x equivalent to v initial t plus half at squared. So this is actually on how, by using calculus, we are going to derive kinematics equation. So that's all. Thank you very much for your time and attention. Please do the tutorial question. See you again.